Here we are, starting a new chapter in our lives. So exciting to start a new chapter. Yay! I'm so excited, you guys. Hopefully you're as excited as I am. Whee! Alright, probably not, but I'm going to pretend like you're all that excited, and here we go. I'm talking about, in this section, it's just kind of an intro to rational expressions. So first of all, what the heck is a rational expression? What is that name all about? So a rational expression, this is the definition. It is a fraction whose numerator and denominator are polynomials. So if you kind of glance at this page here, you see a bunch of examples of these guys. So you see, like, yeah, it just looks like a fraction. It's like you took two polynomials, you Frankenstein them together and popped them into one weird fraction. So believe it or not, there are actually some equations that we need to solve in real life that have these guys in them. So we kind of need to know how these interact with each other, you know, how do you reduce these? I mean, that's what we're really learning in this section is you can think of all these guys as like regular fractions, even though they're polynomials over polynomials. Still, we can do all the same things that we did with fractions. We're going to learn how to reduce them. We're going to learn how to multiply them in another section. We're going to learn how to divide them and then add and subtract them in future sections. So this section, yeah, like I said, it's just first an introduction, and then we're going to learn how to reduce them in this section, and then we're done. And then we'll move on to other things to do with these crazy rational expressions. So, okay, well, yeah, might as well start talking about it. Example 1, this is one of the first things that you learn about rational expressions. It wants you to find all numbers for which the following rational expressions are undefined. So what we want to think about is, keep in mind, when is a fraction undefined? Remember, a fraction is undefined when its denominator equals 0, right? We've seen that before, like if it was 7 over 0, that's undefined. If it was the other way around, 0 over 7, that's 0. That's not undefined. It's only when the denominator is undefined, it's only when the denominator is 0 that you get undefined. So if you want, in these problems, since we have polynomials, we're looking for example, in this very leftmost one, like they're saying, what kind of x value would make that denominator undefined, you know? So really, in other words, when they say that, you can say, what x value, or plural, sometimes there's more than one, what x value or values would cause this to be undefined, but it more specifically would cause the denominator to be 0. So we could guess, like say, okay, well, what could you subtract from 6? Or no, what can you take, subtract 6 and get 0? That kind of thing. You can just guess, but you know what you can just do is grab that denominator and set it equal to 0 and solve for x, and that's it. So that's the idea behind these example 1. If you want to know where a rational expression is undefined, all you do is, set the denominator equal to 0, create your own equation out of it, and solve for x, and solve for the variable, I should say, because it might not always be x. And that'll always work, so that'll tell you what value or values would make this thing undefined. So in this first one, I have x minus 6 equals 0. To solve that guy, I'm going to move the 6 over. And I find that x equals 6, so that must be the value that would make this undefined. And you notice that's true if you think about the original rational expression we were given. What if you put a 6 in for x? In the numerator, it's fine. You'd have 4 times 6 plus 5. That's like 29. So that's fine. It's the denominator, though. If you put a 6 on the bottom, 6 minus 6 would be 0. So you'd have 29 over 0, which is undefined. So they're right. The way we did it is right. We did find the value that would make that denominator 0, which would make the entire rational expression undefined. So really the answer is 6. This part doesn't really matter. It's just kind of me checking in my head. Alright, let's try this next one. So it's a more complicated guy, z minus 7 over z squared minus 6z minus 40. They want to know where that's undefined. But we're going to just do like exactly what we set up here. Set the denominator equal to 0, and then solve for the variable. So you notice the numerator doesn't matter, and that's because what dictates whether a fraction is undefined or not is the denominator. The numerator has no effect on whether it's undefined or not. So really, the numerator could be anything. It doesn't matter. Z minus 7, it could have been anything. It doesn't matter at all. Like it says, I just set the the denominator equal to 0 and then factor it. Like in this one, I have to factor. The last one, I was able to just solve by isolating the variable. But this one I can't just isolate the variable because I see a variable squared here and the variable sitting here next to a 6. I can't solve for z when it's sitting in two different unlike terms. Alright, but if I factor this guy, let's see, I'm looking for two numbers that multiply to -40 but add up to -6. 40 is what? 10 times 4. Oh, actually, that works. That was the first one. But I need the 10 to be negative in order for them to add up to a -6, and the 4 to be positive. There we go, that works. Yeah, because -10 times 4 is -40. Good. -10 plus 4 is -6. Okay, good. Whew. Now I'll set each of those equal to 0. The z minus 10 equals 0. Z plus 4 equals 0, and solve each of those. And those will be my two values that will make this undefined. I'm going to add 10 to the other side to solve the first guy. That'll give me 10 for z. For the other guy, I'm going to subtract 4. And that'll give me -4 for the other z value. Alright, so we found two answers to this second part. Z equals 10 and z equals -4. And if you wanted to, you could check to see that if that's true or not. All you'd have to do is take your original rational expression and replace, like for example, if I focus on 10, what if I put a 10 in for all the z's there? So like we said, the numerator doesn't really matter, it's the denominator that you're worried about. I want to see if he's undefined or not. So just imagine, what if I put a 10 there in the denominator? It's 10 squared. Okay, what's that? 10 squared is 100. I'm going to write that down. And then minus 6 times z, but I'm thinking if z is 10, so it's minus 6 times 10, which is 60. So far, 100 minus 60 is the denominator, minus 40. 100 minus 60 minus 40 is 0. So that's true. If I put a 10 in there, I do get a 0 denominator, which would mean it's undefined. And if you were to similarly check z equals -4, you'd also see that that would make the denominator 0 as well. And that would mean it's undefined. But the way we followed the procedure, you know, we set the denominator equal to 0, we came up with an equation and we solved it. That means that we found every single value that would make that denominator 0. We found two values. There are no other ones that would make that denominator 0. If there were, we would have found them when we solved that equation. So it's kind of amazing, actually, that there are two values out there, and we found both of them, and there are none other than that. It's kind of interesting. All right, let's try this third one here. So same kind of thing. I'm totally ignoring the numerator. I know that all that makes a rational expression undefined is the denominator, so I'm taking that guy and setting him equal to 0. So this one's kind of weird. It's two terms. So at first I thought, what about difference of squares or difference of cubes or sum of cubes? But no, they have a like term, actually. I'm just going to factor the like term out. Hello. Or the common factor. What do they have in common? All it is an m, right? But remember when we said if the leading term is negative, you probably want to factor a negative out as well. So since the higher power term is negative, I'm going to take not only an m out, but negative m. Negative m times 5m would make -5m squared. Negative m times -3 would make the positive 3m. Because you need the negative times the negative to make the positive here. And that's really as far as this one can factor. There's nothing really I can do with what's inside there. There's two terms, but it's not difference of squares, difference of cubes, or sum of cubes. I think that's it. But I think at this point, if we just set each of these factors equal to 0, the outer guy, -m equals 0, and the inner guy, 5m minus 3 equals 0. That'll give us our two solutions. So the left one here, you've got -m equals 0. All I have to do is get rid of that negative. I'm going to divide both sides by -1, and that should do it. It's -m divided by -1 is regular m. 0 divided by -1 is 0, since 0 divided by anything is 0. There's one value that I've got that would make this undefined. Now I'm going to solve the other guy and figure out what the other value is. First I'll add 3 to both sides. That'll mean 5m is equal to 3. And the last step would be divide both sides by 5. And that'll give me my other value of m. So 3/5 must be the other one. I guess so. If I put 0 in that rational expression there, that makes sense actually. You put a 0 here. If you you replace m with 0. 0 squared is 0. 0 times -5 is 0. So this term becomes 0. 3 times 0 is 0. So really, yeah, the denominator would be 0 if I put a 0 there. The 3/5, that's going to be harder to check, but it would work out too. If you replace the m with 3/5, you square it. It's not going to be pretty. You multiply it by the -5 in the front, And you also replace the m next to the 3 with 0. Or sorry, with 3/5. That would also give you a 0. Alright, so that's kind of the thing. I think we're going to kind of keep that in the back of our minds throughout this whole chapter, that we can do all kinds of fun things with these rational expressions. We're going to learn how to multiply them, divide them, add them, subtract them, all kinds of fun stuff. Just got to keep in the back of our minds that these things, they're kind of volatile. We can plug in a lot of different values for the variable, whatever we want. But just keep in mind, like in this first example here, you can't plug a 6 in. That's a no-no. And then in the second one, you can't plug a 10 or a -4 in. That would be bad. And the last one, you can't plug a 0 or a 3/5 in. But as long as you stay away from those values, then these are, fun little rational expressions to play with. We can plug in whatever we want, as long as it's not one of those guys. Alright, but really the main thing about this section is we're going to want to learn, lastly, how to reduce these things. Like fractions, imagine you have a fraction and you want to reduce it. They're very similar, so actually just to show how similar they are, notice the first example we have here at the top left, it's actually a fraction. There's no variables in there. So this is really just an old-fashioned fraction. It's not really, it's not, I don't know if it's really a rational expression like we're used to. It is a polynomial technically in the numerator and denominator, but they're both constant term polynomials, monomials. But how do you reduce those guys? All right, well, what you do is, I don't know if you necessarily write this out, but what you do in your head is you say, all right, look at those numerators and denominators. You say, what can divide into both of those guys, 44 and 64? I think 4 is the most it could be, right? But you know what? In these problems, I think what we're going to want to do, just to make it similar to what we'll do with these rational expressions, I'm actually going to take both numbers, 44 and 64, and factor them into primes. I know that sounds crazy. But what is 44? It could be 4 times 11. 11 is prime, so that's done. The 4 could be 2 times 2. Those are prime, so that guy's done. Alright, so that means the numerator I can rewrite 44 as 2 times 2 times 11. And what we're going to do is we're going to cancel like factors. And then for the denominator is 64. When I see 64, I think of 8 times 8, but you can probably break it up into 8 times 16 or whatever you happen to think of. And each of those 8s is a 2 times a 4. The 2's are prime, but the 4's are not. Got to break the 4's down more into 2 times 2. There we go. That's a lot of 2's, huh? How many 2's is that? 6 2's. Holy moly. So it's 2 times 2 times 2 times 2 times 2 times 2. I think that's 6 of them. Alright, now that it looks like a product, I guess that's what you're trying to do, is make the numerator look like the product of a bunch of kind of prime factors. You've kind of broken down the number as far as it'll go into its building blocks of prime numbers. And the same with the denominator. And now that it's the product of a bunch of things, you're free to cancel any like factors. So that's really what you want to do, and that's what we'll be doing with these rational expressions too. You want to factor numerator and denominator into primes, which, in this example we got actual prime numbers, but in the next coming examples we'll have prime factors. It just means factor it as much as you can. Then cancel like factors. If you see the same factor in the numerator and the denominator, you can cancel them. And then really, once you cancel what they have in common, it's just what's left over in the numerator. Okay, here it's 11. And the denominator, it's 4 2's, but what's that? 2 times 2 is 4, times another 2 is 8, times another 2 is 16. That's really the idea behind it. Yeah, you're going to factor as much as you can, both numerator and denominator, and then look to see if there's any like factors. Other than that, that's really all you're going to do. Cancel them, and then whatever's left over is your answer. So let's try this problem directly to its right. I look at the numerator, t minus 5. I can't factor that. They have nothing in common. T and 5 have nothing in common. It's 2 terms, so the only way to factor it would be if it were the difference of squares, difference of cubes, or sum of cubes, but it's not. That's true. Once in a while, it's kind of like if you had a fraction where either the numerator or the denominator was already prime. Then you can't really break it down. It's just, you got to leave it and hope you see that prime in the other factorization. So t minus 5 on the top is going to stay the same. But in the denominator, I see you got negative 3t and 15. They have a common factor of 3. 3 can come out. But also, I not only want to take a 3 out, I'm going to take a negative 3 out. Because remember, the leading term, if he's negative, you want to factor a negative out as well, since t is a higher power than the constant. So let's see, then if I factor that guy out, negative 3 times what is negative 3t? Okay, that'd be t. Negative 3 times what is positive 15? It'd be negative 5. And now you notice, look at that, t minus 5, the exact same factor on the top and the bottom. So they can cancel. And just like with fractions, if you remember, what if you have either the numerator or the denominator, everything cancels from it. What's left over is a 1. So it's kind of the same thing. And then denominator, we still had the negative 3 left. Yeah, and the 1 is because, I don't know, like, think of an example with actual fractions. Let's see down here. Like if you had 2/8, you know? You could say, like, oh, 2 goes in to 8 4 times. So the denominator is 4, but what's the numerator? It's always a 1. Even though you canceled the entire thing, it's still kind of, you know, we just kind of take it for granted by now because we've done that so many times. But it'll be the same for these rational expressions here. They're kind of nice. If you ever get stuck on these, no matter what section you're in of this chapter, you're like, oh wait, how do I multiply these? How do I reduce them? How do I add them? Just think about regular fractions and then try to model it after that. It's really similar. Okay, sounds good. Let's try this next one here. You got x squared minus 4, okay, over 5x plus 10. So I'm going to try to factor each one first. You definitely need to factor. You can't, so for example, before I factor, I can't go like, oh, 4 and 10, 2 goes into both of those. 2 goes into 4 twice, 2 goes into 10 5 times. You cannot reduce until you factor. You have to factor to make it look like the product of some things. It can't be the difference of some things and the sum of some things. Which, if it's a bunch of terms adding or subtracting, you are not allowed to cancel. It has to be factored and then you can cancel. So that's something very important that's easy to forget. Factor before you cancel. That might even be worth getting a tattoo somewhere on your arm or something so you don't forget. You know, you're taking the test or something. You look down, oh, thank God I got that tattoo. Whew! That was a close one. No, so the numerator, look at that guy. He's x squared minus 4. That's the difference of squares. It's x minus 2x plus 2. So really these problems, if you're really familiar with factoring and you felt pretty good about factoring, this chapter is going to be a lot easier for you. But if you really still are struggling with factoring, I think it's good to go back and work on it. Maybe talk to a tutor or talk to another classmate or just practice more. It'll really help in this chapter as well. So okay, that numerator is the difference of squares. The denominator, 5x and 10, have a common factor of 5. If I factor that 5 out, x plus 2 is left. Because 5 times x is 5x, 5 times 2 is 10. And you notice they have this x plus 2 in common. But that's all they have in common. So the answer, or the reduced form, will be what was left over on the top, x minus 2, over what was left over on the bottom, 5. And at this point, there's not really a need to keep the parentheses around the x minus 2. You know, these parentheses we had here, they were kind of only there to separate it from the x plus 2. But now that the x plus 2 is gone, there's really no need to write the parentheses. I would only leave them if there was more than one factor left over, you know. If it was x minus 2 times something, then I would leave him. But he's all by himself, so there's no need for that. Alright, I think we're on a roll here. So yeah, if you notice, it's all about factoring. The faster you are and the better you are at factoring, the easier these are going to be. I'm looking at the one to the right now. Looking at that numerator, first thing I want to do is try to factor that guy. At first I got freaked out. I said, oh, this is a trinomial with a leading coefficient not 1. Oh crap, we got to use that x method. But no, we don't, because there's a common factor on the top. I can take a 2 out, and then I'll see if I can factor further later. Let's see, okay, if I factor a 2 out, what's left over? T squared minus 3t plus 2. And maybe I'll factor that. You know what, I might go ahead and factor that. I'm going to leave the denominator blank for now. I'm just going to focus on the numerator. There's a 2 outside. That's a trinomial with leading coefficient 1, so there's no need to do the x methods, because the coefficient of t squared is 1. It'll just be a t and a t. And I just have to think about what multiplies to positive 2 but adds up to negative 3. Well, that'd be a negative 2 and a negative 1, or the other way around, negative 1 and negative 2. Alright, I think we factored the numerator as far as it can go. Now he's just going to wait to see what happens with the denominator. So look at the denominator. You got 4t squared, 12t, and 16. They all have a common factor of 4, actually. So if I take a 4 out, what's left over? 4 times t squared would make the first term. 4 times 3t would make the second term. 4 times negative 4 would make the third term. And I think that trinomial in there can be factored further. Let's see, I'm going to leave the 4 outside. Don't forget about that guy. He's going to affect the problem. Since it's a trinomial with leading coefficient 1, I'll just have a t and a t. And I'll look for what are the numbers that multiply to negative 4 but add up to positive 3. Well, that'd be a positive 4 and a negative 1. Or the other way around, negative 1 and positive 4. Those are the guys. Alright, now that I've factored it as far as I can, I'm going to see what I can reduce. What do we see here? Well, they have a t minus 1 in common. There they are. And we know we just got kind of lucky that the t minus 1s are directly above each other. If they weren't directly above each other, like if this guy was the t minus 1, then of course you can cancel them. They don't have to be directly above each other to cancel. As long as the factor is there somewhere in the numerator and somewhere in the denominator. So t minus 1s were similar. This factor here, t minus 2 and t plus 4, they're completely different. So I can't cancel them. And notice you cannot cancel a part of it, like this t and this t. It cannot be cancelled because the t in the numerator is part of the factor t minus 2. That's a package deal. That's one whole thing. And the t in the denominator is part of the t plus 4. That's, again, another package deal. You can't cancel part of a factor. It has to be the entire thing or none of it. But the 2 and the 4 in the front, they can actually be reduced as if they're normal fractions. 2 goes into 2 once, 2 goes into 4 twice. I think that's all we can reduce. So now I just think about what's left over on the top. You got the 1 times the t minus 2. That's really just t minus 2. The 1's not really necessary. And on the bottom, I'm actually left with 2 things. I have the 2 times the t plus 4. That's why I'm leaving parentheses on the bottom, because t plus 4 is being multiplied by something. And at this point, you know what? It's not really worth distributing that 2. You can just leave it as is. In this section, I don't think they don't really care about you distributing stuff. Just once you get your answer, don't worry about it. Just leave it as separate factors. No need to multiply it out. Yeah. So I think so far so good. Like, as you can probably tell, it's all about factoring. If you factor correctly, you're probably doing pretty good in this section. Just being careful. Alright, let's move on to the bottom left problem here. This n to the 6 plus 27 over n squared plus 3. That one looks kind of tricky. So let me kind of focus on the numerator there. Alright, n to the 6 plus 27. There's no common factor, so I can't factor a greatest common factor out. It has 2 terms. The n to the 6 is one term, the 27 is another term. So the only methods I could use are difference of squares, difference of cubes, or sum of cubes. But that's a plus sign in the middle, so it can't be a difference of squares, because difference of squares has to have a minus in the middle. Similarly, it can't be difference of cubes, because difference of cubes means there's a minus in the middle. This guy's, the only hope it has is it's got to be the sum of cubes. And I think it actually is, because n to the 6, think about that guy, he could be something cubed, right, or something to the 3rd power. That's n squared to the 3rd power. And then 27 is actually 3 to the 3rd power. So those are actually things, cubes or things to the 3rd power. But maybe just to remember how that works, if you remember there's a formula for it, the sum of cubes. You can always look back at your notes, to look at this while you're doing your homework, but the sum of cubes formula was if you have a cubed plus b cubed, it's kind of what we have, something to the 3rd power, and then plus something to the 3rd power. It factors into a plus b, parentheses a squared minus ab plus b squared. We're going to have to use that guy. And I guess we're thinking of our a as n squared, because we've already identified that the first term, n to the 6, we're saying, what can you cube and get that guy? Well, we wrote it out. It's n squared. N squared to the 3rd power is n to the 6th. And then 27 is, you say, okay, b is what can you cube and get 27? Well, we wrote that out as well. 3 would be b. So all I have to do is replace, in this little formula here, like we've done before, replace the a's with n squared and the b's with 3. Maybe I'll do that below, because I didn't really leave myself a lot of room there. Oops. Let's see, so a plus b, alright. And then a squared minus ab plus b squared. Alright, so what was a again? A is n squared. So where all the a's were, I'm going to put n squared here, n squared here. And then b was 3. So where all the b's were, I'm going to put a 3. 3 here, 3 here, and 3 here. I might as well clean that up while I'm at it down here. There's nothing I could do in the first parentheses. That's as good as it gets. N squared plus 3. Then here, n squared to the 2nd power, you multiply the powers and get 4. and then minus n squared times 3. I'm going to write 3n squared. And then plus 3 squared is 9. There we go. Alright, all that work just to say that's how the numerator factors. N squared plus 3. Alright, I'm going to just transfer that up here. And then it's n to the 4th minus 3n squared plus 9. That's the numerator. And the denominator, you know what? I was going to say, oh, can I factor that denominator? You know what? It actually doesn't matter because the denominator cancels with the factor on the top right there, the n squared plus 3. But even if you think about it, that guy will not factor because n squared and 3, they have nothing in common. There's no greatest common factor. And there's two terms, so it's got to be either difference of squares, difference of cubes, or sum of cubes. But those two terms don't fit any of those bills. It's not a difference of squares, because a difference of squares would have to have a minus, and plus 3 is not a square. And then it can't be difference or sum of cubes, because those two terms are not cubes. So that denominator didn't cancel, or didn't factor anyway, it wouldn't matter. So since the numerator and denominator have something in common, they cancel, all that's left in the numerator is n to the 4th minus 3n squared plus 9. The denominator you can think of as, there's a 1 left, but if you remember, anything over 1 is that thing. So it really just ends up being kind of like this whole number with no denominator left since the whole denominator canceled. So be careful, this one, everything from the denominator canceled, which kind of made the denominator disappear. But that's not true when the numerator disappears. So notice, like in that second example we did up here, it was t minus 5, and it ended up that everything in the numerator canceled, but that did not mean the numerator disappeared. The numerator became a 1. So be careful, it's only when the denominator disappears that you can drop the denominator. When the numerator disappears, that just means it's a 1. It doesn't disappear altogether. So be a little careful. I think I've seen that mistake made before. Let's look at the next one. To its right, I see a squared minus 1 over a minus 1. Well, a squared minus 1, I think that's a difference of squares. Because a squared is, of course, a square. 1 is itself squared. And that denominator a minus 1, there's nothing I can do with that, because it has two terms, a and 1. They have nothing in common. It's not a difference of squares. It's not a sum of cubes. It's not a difference of cubes. So I think the denominator is you're just gonna hope that the numerator has the same factor in it. The denominator does not reduce, or factor. So in the numerator, I asked myself, what can you square and get a squared? That would be a, so he goes in the first spot. And then what can you square and get 1? Well, of course that'd be 1, because 1 squared is 1. And now that I see the factorization, I realize, oh, okay, the numerator and denominator both have an a minus 1 in common. And all that's left is an a plus 1 in the numerator. Since the denominator, if you want, you can write it, just to be safe, you can say, oh, it's a plus 1 left over on the top. Let's see, a plus 1. On the bottom, there's nothing left, so I put a 1. But we know that any fraction with a denominator of 1 can be written as kind of like a whole number, without the denominator. So you could take that extra step to write the over 1 and then decide, oh, it's just like a whole number or something that doesn't need a denominator. Well, you can just skip the step if you want and go straight to a plus 1. That's fine. Alright, we're doing good here. I think if you notice, the difficult part is really just factoring. If you have factoring down, then you're fine, but if you don't, then it's kind of tricky. Alright, let's try the second to the last one. The numerator, t squared plus 2t. I notice they have a common factor of t. I'm going to factor that out first. If I take t out, t plus 2 is left. And I think that's as far as that numerator can go, because t plus 2 can't be factored further. If I look at that denominator, 2t squared plus t minus 6. So there's no common factor there that can be factored out. Oops, what else? What else? It's a trinomial with leading coefficient not 1. It's 2. So you know what? Unfortunately, I might have to go off to the side or down below and factor this, because I have to use that x method, unfortunately. Yeah, that's not going to be fun, but oh well. We got to do what we got to do. So I got to say, what's a times c there? A is 2, and c is negative 6. A times c, 2 times negative 6 is negative 12. So I want to know what multiplies to that, but adds up to the middle coefficient, a 1. So okay, let's see. What adds up to 1, but multiplies to negative 12? I think that would be a 4 and a negative 3. Or the other way around, negative 3 and 4. Doesn't matter what order they're in. But those are the guys I want. Alright, that means that when I rewrite this trinomial here, I'm rewriting the first term the same, 2t squared, and the negative 6, but the middle term is going to be split up into something t, where those somethings are the coefficients I just found, the 4, positive 4, and the negative 3. And now that I've rewritten it, I'm going to factor by grouping. So let me see, I'm going to break this down the middle and say, alright, between the first two terms, what do they have in common? They have 2t in common. If I factor 2t out, what's left? It would be t plus 2. And what do the third and the fourth term have in common? Negative 3t and negative 6 have a negative 3 in common. Negative 3 times what would be negative 3t? Would be a t. Negative 3 times what would be negative 6? That'd have to be a positive 2. Alright, things in parentheses are the same. That means I've done something right so far. I'm going to factor that part out. T plus 2. If I take t plus 2 from the first term, the leftovers are 2t. If I take it from the second term, negative 3t is left. Or sorry, just negative 3. Alright, that's the factorization of the denominator. Now I'm going to bring that back up. Take this guy and put him in that denominator there. T plus 2, and then 2t minus 3. Ah! Whew! It's a good thing we did that, because they have that common factor of t plus 2. Nice, but nothing else can cancel, because remember, even though there's a t here, it cannot cancel with this t downstairs, because that t is part of a factor of 2t minus 3. It's a package deal, and part of it couldn't cancel. It'd have to be the whole thing. The only way that denominator could cancel is if you saw that entire thing on the top, 2t minus 3. So that's it. It's t over 2t minus 3. Don't try to cancel it anymore. Again, think of 2t minus 3 as one item. You can't cancel part of it. It has to be the entire thing. So there it is. Alright. Ah, we got one last one, and it looks so simple, but it's kind of a weird concept. Notice the last guy, he's x minus 8 over 8 minus x. So they seem like it's almost the same factor. You got an x on both, you got an 8 on both. So can't they just cancel? No, and remember that you cannot cancel until you factor. So I could not say, oh, the x's cancel and the 8's cancel. I wish you could do that, but remember, you cannot cancel until you factor. So the trick on this one, if you notice, I think they call these guys opposite factors. The x minus 8 and the 8 minus x, and they say they're opposite factors because you notice they have the same terms, x and 8, but they have opposite signs. Because x minus 8 has x positive and 8 negative, whereas 8 minus x has 8 positive, x negative. So they have opposite signs. If you see those guys, if you see opposite factors, you say, look, they have the same terms, but opposite signs. X is positive on top, x is negative on the bottom. 8 is negative on top, 8 is positive on the bottom. What you want to do is factor. It seems kind of random, but it works. Factor a negative 1 out of one of them. What's left should cancel, basically. I know that's probably not correct grammar, but you know what I mean. Alright, that's up to you. You just factor a negative 1 out of either one. Just don't factor negative 1 out of both. It's just either or. It doesn't really matter, but for me, I kind of like x minus 8 to me looks normal. The denominator kind of freaks me out. 8 minus x. I don't like that. It's like, x is supposed to come first. What are you doing, 8? Why are you trying to be weird and stuff? Anyway, I'm going to factor a negative 1 out, like it says. Because pretty much, what happens when you factor a negative 1 out? It pretty much just changes everybody's signs. And because they said they have opposite signs, if I change their signs, they'll now be the same as the numerator signs. So okay, I'll ask myself, negative 1 times what is the 8? That would have to be negative 8. Because negative 1 times negative 8 would make positive 8. And then negative 1 times what is negative x? It's positive x. Alright, and at first I look at it and say, why was that a good idea? But now look at the denominator, rearrange the terms that are in the parentheses. Negative 1's outside. What if I write the x first? It's x minus 8. And notice now those are the exact same thing. So they cancel. And the numerators, everything canceled, that means there's a 1 left over. The denominator, everything cancels except the negative 1. So you're left with 1 over negative 1. But 1 divided by negative 1 is negative 1. So it's crazy, but the answer is negative 1. And you wouldn't have got the right answer if you had just canceled. Remember, at the beginning, it was x minus 8 over 8 minus x. If you had just said, oh, let me see, the x's cancel, the 8's cancel, so it's 0, or something. I don't know how people would have canceled it, but it wouldn't have worked. Your answer is supposed to be negative 1, and if you canceled individual terms, you can't do that. But if you tried to cancel individual terms, you would not get negative 1, that's for sure. So be careful on that. That's not really that important, but once in a while, if you come across a problem like this where you say, you know what, those are those opposite factors that I heard about. What do I do again? You can kind of look back at your notes and say, oh yeah, that's right, you factor a negative 1 out. Okay, and then everything works out and it's beautiful. we'll probably revisit that idea in coming sections. We'll see those opposite factors again, just to kind of remember what they look like and what to do with them. But I hope everything made sense in this section. It's kind of weird, but like I said, I think it's all about factoring. If you're good at factoring, the section's okay. If you're bad at factoring, it's going to be sort of painful. But if you're not great at factoring, this section's probably going to make you better, because you're forced to practice it every problem. So alright, thanks for listening. In the next section, we'll do even more fun things with these. Alright, talk to you later.